Welcome back to Tales of Chemistry. Today, let us see some mixed questions from mole concept and stoichiometry. So, I have included questions from mole concept, then LUSSAC'S law, also empirical and molecular formula. Now, look at the first question. 1 mole of a compound contains 1 mole of carbon, meaning in your compound there is C, 1 mole of carbon. And along with this, 2 moles of oxygen are present. So your compound is nothing but carbon dioxide. What is the molecular weight of the compound? Carbon's weight is 12, atomic weight is 12, and oxygen's atomic weight is 16. You have 2 such oxygen atoms. So 12 plus 32, that is 44. The same can be asked as what is a vapor density? Whatever is the molecular weight, half of it is vapor density. So if vapor density is asked, the answer will be 22. Now, moving on with the second question. Second question is very simple. Empirical formula of a compound is CH, or empirical formula CH. Then, what is molecular formula if the molecular weight is 78? Now, let's quickly find out the empirical formula weight. Empirical formula weight is 12 plus 1, that is 13. Now, we need the integer. N is molecular weight by empirical formula weight. Molecular weight is given to us 78. 78 by 13, which is equal to 6. So the integer is 6 and empirical formula 6 times is the molecular formula, which means CH 6 times, that is C6H6. Okay, this is called benzene. C6H6 is benzene. Moving to the third question. If 2 compounds have same empirical formula, but different molecular formula, empirical formula is the same, but molecular formula is different, then they must have different percentage composition? No, because if the percentage composition is different, empirical formula itself will be different. But here it is given same empirical formula. Different molecular mass, that's a possibility, because different molecular mass meaning the integer that you calculate will be different. Integer n, which is molecular mass by empirical formula mass. When molecular mass is different, n value will be different. And when n is different, the molecular formula will also be different. Same vapor density? No, wrong. When vapor density is same, molecular mass is same. And when molecular mass is same, then both compounds should have the same molecular formula. Same percentage composition? Yes, but because the percentage composition is same, you got the same empirical formula. So percentage composition has got nothing to do with the molecular formula. Though the statement same percentage composition is correct with regard to empirical formula, but the question here is to find out why are they having different molecular formula. So that's not because of percentage composition, but because they have different molecular mass. Which has same percentage of carbon? Looks a little lengthy calculation, but we can still solve it easily because we are not sitting and calculating the percentage accurately. So, which has the same percentage of carbon? In the first case, that is A, acetic acid. Acetic acid has 2 carbons. So percentage will be 24 by the molecular mass of acetic acid is 60. Molecular mass of acetic acid is 60. So this is 24 by 60 into 100. And the other one is 24. Again, 2 carbons are there. And ethanol's molecular mass is 48. Now, since the numerator is the same, okay, and denominator is different, this is not our answer. Definitely, they don't have the same percentage of carbon. Moving on to B, acetic acid. I just calculated in the first case, so I'm just copying it. 24 by 60 into 100 and C12H22O11. 12 into 12, you have 12 carbons. So this is 144 into 100 divided by around 342. 342 is the molecular mass. Now, here I will have to simplify. Okay, so what I'm planning to do is just calculate or divide that 342 by 12. So it is 28.5. So this is 12 into 100 by 28.5, and this one will be, even if I divide them by 2, 12 into 100 by 30. Now these two are not the same. Okay, so no further calculation is required. I'm just concluding that even option B is not the answer. For option C, first one, cane sugar. So it is 144 into 100 by 342. And the second one is C6 means 72. 72 into 100 by 180. Okay. So again, you can prove that even if you divide 144 and 342 by 2, okay, so you are not getting a closer value or same value. Now, our entire hope is on the last question. You can try this. You can prove that these two are not the same. Now, moving on to the option D, C6H12O6. So that is 72, right? 72 into 100 by 180. And acetic acid is 24 into 100 by 60. Now, let us make the denominator the same, 60 and 180. So, if I divide 180 by 3, divide 180 by 3, the answer will be 60. So then I will have to divide 72 also by 3. So let's do that. 72 by 3 is 24. So here the final answer, which has the same percentage of carbon, option D is the correct answer. Therefore, if such a question comes, you don't have to solve the actual percentage of carbon, but you can just compare them and find out which is the correct answer. Next one, calculate the percentage of nitrogen in ammonium nitrate. Formulas not given. We should know the formula. NH4NO3. Nitrogen's atomic weight is 14, H is 1, O is 16. This will most likely be given to you. Now, question is to calculate percentage of nitrogen. So first of all, we need to know the molecular mass of ammonium nitrate, which is 14 plus 4 into 1, 4 plus again 14, okay, plus 16 into 3. So, on adding up all this, we get 80 grams ammonium nitrate's molecular weight is 80. Then percentage of nitrogen is, there are two nitrogens, right? So 28 by 80 into 100. On solving, this is 35%. Okay, that was a simple question. Now, this is something different. Under same conditions of temperature and pressure, one collects 2.2 liters of carbon dioxide, 3.3 liters of chlorine, 5.5 liters of hydrogen, 4.4 liters of nitrogen, and 1.1 liter of sulfur dioxide. Different gases are collected, but under the same conditions of temperature and pressure. In which sample there will be the greatest number of molecules? Well, this is very easy to calculate because we have studied this. Equal volume of all gases under similar conditions of temperature and pressure, okay, contains equal number of molecules. Equal volume of all gases contains same number of particles, which means the gas which is present in a higher volume will have the more maximum number of particles. Which one has the maximum volume here? 5.5 liter of hydrogen. So your first answer is 5.5 liters of hydrogen, Avogadro's law. Then which one is present in the lowest volume? 1.1 liter. 1.1 liter of sulfur dioxide. So it's not the gas. It's not whether you're talking about carbon dioxide or chlorine or hydrogen. It is just about the volume. Equal volume under similar conditions of temperature and pressure will contain equal number of particles. So if you consider X particles are present in SO2, 2X particles will be there in CO2, 3X in chlorine, 4X in nitrogen, 5X in hydrogen. That is all. Moving on to the next. 16 grams of oxygen and 3 grams of hydrogen are mixed and kept in a vessel. Look at this question now. It's not told to us that it is burnt. It is just mixed, which means they are not reacting. What you have is a mixture of 16 grams of oxygen and 3 grams of hydrogen at 760 millimeter, meaning 1 atmosphere of pressure, 1 atm pressure, and the standard temperature. So basically, they mean to say that these two gases are mixed at STP. What will be the volume of the mixture, total volume of the mixture? So let's first find out volume due to the first one, 16 grams of oxygen. Volume due to 16 grams of oxygen. Okay, what is the standard statement? 32 grams of oxygen at STP has a volume of 22.4 liter. But here 16 grams is taken. 16 grams of oxygen at STP will have X liter. So on solving here, you will find that X is equal to 11 by 2 liters. Okay, 11 by 2 liters. So volume due to oxygen is 11.2. But there is 3 grams of hydrogen also. So volume due to 3 grams of hydrogen is to be calculated. 2 grams of hydrogen. What is this 2 gram? Molecular mass of hydrogen. 2 grams of hydrogen will have 22.4 liters. Therefore, 3 grams of hydrogen will have X liter and X will be Here 3 into 22.4 divided by 2. That is 33.6 liter. And the question is to calculate the total volume. Total volume will be this 33.6 plus previous 11.2 liter. So when you add them together, okay, 44.8 liter will be the net result here. All right, 44.8. Now, moving on to the next question. Find the number of molecules in 3.2 grams of sulfur dioxide. All right, number of molecules. So first of all, I need the molecular weight of sulfur dioxide. If we follow our approach here, the compound is sulfur dioxide. Relation is between its mass and molecules. Okay, so RMM is to be connected with Avogadro's number. Molecular weight has to be calculated. 32 plus 32, which is 64. Therefore, 64 grams will contain 1 Avogadro number, 6.023 10 to the power 23 particles. But what is given to us here? 3.2 gram. 3.2 gram will have X number of particles, and X will be equal to 3.2 into 6.023 10 to the power 23 divided by 64. And the answer, this on solving, gives us 0.3012 10 to the power 23. Okay. Or else, if not this, what else you can do is just divide 3.2 by 64. So you are getting 0.05. Okay, so leave your answer as 0.05 into 6.023 10 to the power 23 molecules. You don't actually have to multiply it with Avogadro's number. 0.05 Avogadro number of particles are present. Okay, now the next question. 80 centimeter cube of methane is mixed with 200 centimeter cube of pure oxygen at room temperature and pressure. Mixture is ignited and it burns as per this equation. So let's quickly write the Gay-Lussac's relation. X, 2x, and it again gives you X and 2x. Just cross-check whether this equation is balanced correctly. X and 2x. Let's check. 1 carbon on either side, 4 oxygens, 2 plus 2, 4 oxygen on either side, 4 hydrogen. Yes, it is balanced correctly. 80 centimeter of cube of methane is taken. So if I take X is equal to 80 centimeter cube, I need 2x oxygen. 2x meaning 2 into 80, 160 centimeter cube of oxygen is needed. Do I have that? Yes, I do have, which means this is correct. Volume of methane is 80 centimeter cube and volume of oxygen consumed. Volume of oxygen consumed is 2x, which is 160 centimeter cube. Then volume of oxygen unused. Volume of oxygen unused is 200, that is given, minus 160, that is 40 centimeter cube. Also, resultant composition is the question. So we need to calculate the volume of carbon dioxide. Volume of carbon dioxide is X, which is again equal to 80 centimeter cube. Volume of water will not be considered because it is mentioned in the question that it is cooled to room temperature. Okay. Okay. So this was there in the question, cooled to room temperature. Okay. So water vapor will condense to liquid water. Final answer is resultant composition is equal to 40 centimeter cube of oxygen and 80 centimeter cube of carbon dioxide. All right. Now, one last question. Calculate the empirical formula of the compound having sodium 37.6% and silicon 23.1%. Finally, oxygen 39.3%. Atomic weights, sodium is 23, silicon is 28, and oxygen is 16. Next is to know the relative number. Relative number is percentage divided by atomic weight. So let's quickly write that. 39.3 by 16. Now, on division, 37.6 by 23 is around 1.63. I'm just solving it for the second decimal place. 23.1 by 28 is 0.83. And the last one, 39.3 by 16 is 2.46. Now, in the simple ratio, I need to look for the least number from these numbers. So the least number is 0.83. Divide all the numbers by the lowest. And last one, 2.46 by 0.83. So this is 2. This is 1 and 8 3s are 24. So this is 3. What is the question? Just to calculate the empirical formula. So the elements are sodium, silicon, and oxygen. Number corresponding to sodium is 2, number corresponding to silicon is 1, and corresponding to oxygen is 3. Therefore, the empirical formula is Na2SiO3. That is it. Hope you have understood whatever we have discussed today. Stay tuned for more videos.